In the first video in this series, I briefly explained what DCC was and how it differed from direct current control of model trains. In part 2, I want to explain what a packet is and how packets of data are used in DCC systems to control trains and to send information to trains. You saw this overhead in the previous video. On the left is a DCC controller with a model train sitting on a track, and inside the model train is a DCC decoder. The DCC controller through the tracks sends a packet of data to the engine, which is picked up by the DCC decoder, converted into control signals for the train. It's the DCC decoder that commands the train to go faster or slower, or to stop or reverse, or to turn its lights on, or to blow its whistle, or whatever the operator of the model railroad wants it to do. In this example, in this video, I want to explain how a packet of data is made up and what the fields are made of. There are various formats for packets depending on how complex the layout is, but in my setup I've used the simplest possible packet specified by the National Model Railroad Association, which consists of 4 different fields: the preamble, the address of the engine, the command, and at the end the error check. And the data in each of these 4 fields is sent as a series of zeros and ones down the track. So first of all, the preamble. The preamble is a series of 12 ones. And in DCC, the only time you'll ever get a series of 12 ones is in a preamble. The preamble tells the DCC decoder that it's about to receive a packet of data. So a preamble, in a sense, is, hey, DCC decoder, there's a packet just about to arrive. After the 12 ones in the preamble, the DCC controller sends a digital 0, and the digital 0 tells the DCC decoder on the engine that the preamble has finished and it's about to receive the next field, which is the address of the engine. Next comes an 8-bit field. Remember, the preamble is 12 bits. Next comes an 8-bit field, which is the address of the engine. And in my example, the address of my engine is 6011 in binary, which is equivalent to 3 in our normal counting systems. And whenever you buy a DCC decoder, the default address is always 3. There's no exceptions to that. And if you have more than one engine on a track, or one engine or 2 engines, and other decoders used to, say, operate points or to operate a level crossing, then you need to change the address on each of these to something other than 3. After the address of the engine, the decoder sends out a 0, and the 0 tells the decoder, or sorry, the controller sends out a 0. Now, and the controller sends a 0 to the decoder to say that the address of the engine has been transmitted, and next is come the command. The third field again is 8 bits long, and in my scenario the command is 011011110, and each of these zeros and ones tells the DCC decoder to do something different. So we'll go through these in turn later. After the command, another 0 is sent, and then the error check. The error check is used by the decoder to to ensure that the packet was received without any corruption in it. Just before the packet of data is sent by the DCC controller, it does a calculation on the data in the address field, on the data in the command field. I'll go through this calculation later. And it puts the results of that arithmetic calculation into the 8-bit error check field. The DCC decoder, when it receives the packet, it repeats this calculation on the address field and the command field and works out its own error check. If the error check calculated by the decoder is the same as the error check sent out by the controller, then the decoder knows that the packet was received without errors in it. Can I name a situation where errors would be made in the transmission of the packet? Suppose the engine is going across points when the packet is received, and as it goes across the points, there's momentarily a poor connection between the wheels of the train, or wheels of the engine, and the track. So some of the bits may not be received. So the packet will be received corrupted, in which case the error check would detect that. At the end of the error check, the DCC controller sends out a 1 bit, and this tells the decoder that this is the end of this packet. Now, why do we need to tell the decoder that it's the end of a packet? Because if you look at the NMRA DCC specs, some packets are 5 fields long or 6 fields long. So you need to tell the decoder when the end of the packet is, because it may be expecting other fields. You need to tell it it's a 4-field packet. In my scenario, I had the preamble of 12 ones, a 0. I had the address, which is 6 zeros, 1 1, and another 0. Then a command and a 0. Then the error check and a 1 to indicate the end of the packet. Now, I mentioned that the preamble, which is 12 bits long, is the only time ever the DCC decoder will pick up 12 ones in sequence. Now, assume the address field was 8 ones and the command field was 8 ones, and you could say that's 16 1 bits. But remember, immediately after the 8-bit address field, a 0 is transmitted before the command field is transmitted. So in the normal day-to-day operation of DCC, apart from the preamble, the most ones you can ever get in sequence is 8 ones. So if it receives 12 ones, it knows immediately it's a preamble. Okay, so what do all these zeros and ones means? I've explained some of them already. I won't go through the preamble, I've done that. The address is 6011. If you have more than one decoder in the layout, you need to change one of the addresses, and you change that using the DCC command track. Okay, so a common number to change the address to is the number on the side of the engine. If the engine number is, say, 573, convert that to binary and put 573 in here. And that's a common way of making up the address. Although you can just convert it to 4 or 5 or 6 if you wish. Receives the address in the packet. If the received address is the same as the address in the decoder, it knows that that packet is destined for itself, so it will then wait for the command and act on the command. If the address packet is different to the address of the decoder knows that this packet is not intended for itself, it's intended for some other DCC decoder on the layout, and it'll ignore the packet and just wait for the next one. the command now. This is a bit more complicated. I'll go through this in more detail. Now, there are very many different commands that can be used in DCC. You can tell the train to go forward, backwards, increase its speed, stop, put lights on the front of the back of the engine, blow its whistle. You can tell the decoder if it's part of level crossing to open or close a level crossing, if it's controlling points, to turn points one way or the other. There are many things you can do with a DCC command packet. This one in particular is a speed packet. It's telling the engine to alter its speed. If the first two digits 0 and 1 of the packet, or the first two digits of the packet is 0 and 1, the decoder immediately knows this is going to tell the engine to change its speed or to keep on at the same speed. The third bit, 1, is going to tell the engine if it's 1 to go forward, if it's 0, it's telling the engine to go backwards in reverse. The fourth bit is sometimes not used with the speed command. It's optional depending on the manufacturer. If it is used, it's for very fine granularity in the speed. But it makes no, if your DCC controller sends out a 0 and your DCC decoder doesn't implement it, it makes no difference, you just ignore it. The next 4 digits, in my case 1110, tells the decoder what speed it wants the engine to go at. I've already said it's a speed control. I've already said here in the third bit it's a 1. So I'm saying I want it to go at speed 1110. 1111 is to go at full speed. If it's 1000 here, it's to go at half speed. And if it's 4 zeros, the train is to stop. So with this combination of 4 digits, I can have 16 different speeds in a forward direction. And by changing this to a 0, I can have 16 different speeds in the reverse direction. So 011 here is a speed command forward or backwards. If there was some other digits in here, like 100 or 111, or then the decoder, when picking up the command, will say, this is a command to turn the lights on, or this is a command to blow the whistle, or if it's attached to points, it would say, this is a command to move the points. There are many different commands you can use, and they're all set out in the NMRA DC specs, which I'd encourage you to read. The error detecting bits at the end, this last 8-bit field, DCC uses something called the exclusive OR, or EOR, which is an arithmetic calculation to calculate the error check field. So the controller, before it transmits the packet, calculates the exclusive OR and attaches it as the 4th field in the packet. The decoder, when it receives the first 3 fields, it recalculates the exclusive OR number and compares it with the exclusive OR number received from the controller. If the 2 packets are the same, it'll say this packet has been received correctly, it's not corrupted. If the 2 fields are different, it'll say this packet was corrupted in transmission. It'll reject it and just wait for the next packet to be transmitted. If a packet is corrupted and is discarded, it doesn't matter, because the DCC doesn't just send out 1 packet. It'll keep repeating the packet over and over. Even if there's no change to the speed of the train, it'll keep repeating the packet maybe every 10 milliseconds. So the fact that 1 packet is corrupted isn't going to affect it. The next packet that comes along maybe 10 milliseconds later will carry exactly the same information. Okay, so how do we calculate the exclusive OR? So we have this table here. The address 6011, I've got on the top line 6011. Then I've got the command 011011110. I've got here 011011110. So what exclusive OR does is it does it bit by bit. If the first digit of the address and command are both zeros, the exclusive OR is 0. If the first bit of the address is 0 and the first bit of command is 1, the exclusive OR is 1. If the first bit of the exclusive OR is 1 and the command bit is 1, the exclusive OR is 0, and so on. Okay, or to simplify it, make it more generalized, if the address and control bits are either both 0 or both 1, the exclusive OR bit in the error field will always be 0. If the address bit is 0 and the command bit is 1, the exclusive OR bit is 1. If the address bit is 1 and the command bit is 0, the exclusive OR bit is 1. So this is how the error check field is calculated in C++, which, as you know, is the programming language to program Arduinos. Exclusive OR is the operator hat. If you have two fields with hat between them, effectively you're instructing the C++ code to work out the exclusive OR value between the two numbers. Okay, some more parts now. Suppose we're transmitting 6 packets to this engine. If the controller transmitted lots of packets or a gap in between, it immediately after packet 1, it transmitted packet 2. Immediately after packet 2, it transmitted packet 3, and so on. The decoder would not have time to process the information in packet 1 before it started receiving packet 2, and so on with packet 3 and packet 4. So there must be a gap, a time interval between packet 1 and packet 2, between packet 2 and packet 3, and so on, if the decoder is not to be overloaded with data and stop working. So according to the DCC specs, between packet 1 and packet 2, there must be at least a 5 millisecond delay. Between packet 2 and packet 3, there must be at least a 5 millisecond delay. And the way DCC does this, and the way I've done it in the Arduino code, which I'll explain to you in a later video, it sends out what's called 2 idle packets. An idle packet is a similar 4-field structure to a control packet or command packet, but there's no information in it. And an idle packet lasts just over 2.5 milliseconds. So sending 2 idle packets in between packet 1 and packet 2 produces this 5 millisecond delay. The decoder, on picking up an idle packet, realizes immediately it's an idle packet and does nothing with it. So how are idle packets different to control packets? As I mentioned, idle packets are used to insert delay between command packets. They do not contain any information, but even if there's 2 packets to the same decoder transmitted immediately after each other, or if there's a long gap between packets sent to a decoder, the DCC controller will continuously send out idle packets. And it does that because the DCC decoder always needs to put packets, whether they control or idle, onto the track to power the engine and to power the DCC decoder. If it just sent a control packet and then nothing on the track, the engine would stop, and the decoder would stop working because there's no power on the track. So it puts power on the track continuously by transmitting idle packets. But putting command packets onto the track also transmits power. In my control packets, I've explained the structure here. The structure of an idle packet again is 12 ones, a 0. The address for an idle packet is always 8 ones and a 0. The command in an idle packet is always 8 zeros, then a 0. And the error check is always 8 ones followed by a 1. When the DCC decoder picks this idle packet up, it knows it's an idle packet and just ignores it. So that was the packet structure of DCC. It's quite straightforward. In the next video, in this series, I'll explain how this is implemented in DCC. Video 3, first of all, though, explains how the Arduino motor shield works. So the motor shield, there's a lot of connections on the Arduino motor shield, some of which are used for DCC and some of which are not. So I'll explain how the motor shield works once it's connected to an Arduino Uno processor, and what each of the terminals on it and how it's used to send commands, DCC commands, onto the track to control the train.